Muy buenas tardes a todos en el instituto, en la UNAM, en donde sea que estén, y bienvenidos sean a este seminario institucional en el cual vamos a presentar una de las cátedras distinguidas de la Sociedad Geológica de América para el 2020. En esta ocasión tenemos el gusto de presentar a John Eichelberger, profesor emérito de la Universidad de Alaska. John se educó en geología y petrología ígnea en el MIT y en la Universidad de Stanford. Él es conocido a nivel mundial por sus contribuciones para entender la mezcla de magmas y los procesos de degasificación. La carrera de John incluye laboratorios de investigación, academia y el gobierno de Estados Unidos de América. John tiene una añeja pasión por las perforaciones y la cooperación internacional, las cuales son componentes importantes para explorar el subsuelo de los volcanes. En 2015 recibió la medalla Soloviev, la cual es entregada por la Unión Europea de Geociencias a investigadores con contribuciones relevantes en peligros naturales. Este año, John es uno de los dos Distinguished Lecturers escogidos por la GSA para informar a la comunidad científica sobre la perforación científica continental. Les pedimos que hagan sus preguntas, que escriban sus preguntas en el chat. También, si están ustedes conectados en YouTube, que nos hagan sus preguntas. Nos esperemos al final para ver toda la presentación y que después podamos hacer las preguntas y discutir con el ponente. Voy a repetir exactamente lo mismo que he dicho en inglés, solo en caso de que haya algún compañero del Smithsonian que se les invitó para que atendieran esta plática y para que John escuche la presentación que decimos de él. Welcome, everybody, to the Institute of Geophysics seminar. Today, we are pleased to present John Eichelberger, Emeritus Professor at the University of Alaska. John received his education in geology and igneous petrology at the MIT and Stanford University. He is perhaps best known for scientific contributions in understanding magma mixing and degassing. John's career spans research laboratories, academia, and the US government. He has long had a passion for drilling and international cooperation, both of which are required to explore the frontier beneath our feet. In 2015, John received the Soloviev Medal in Natural Hazards from the European Geoscience Union. This academic year, he is the one of two distinguished lecturers chosen by the Geological Society of America to excite and inform the research community about continental scientific drilling. If you have any questions, you can write your questions on the Facebook chat. And if you're watching us in YouTube, you can also type your question and we will filter all those questions, and then at the end we will discuss with John his research. So welcome, John, to the Institute of Geophysics, and the audience is all yours.
Thank you very much, Giovanni. Can you hear me okay?
I can hear you, yeah, sure.
Well, it's great to be here, even if only virtually. I visited your excellent university before and was treated to a wonderful field trip to El Chichon, and I think it's called Tacana. It's on the Guatemala-Mexican border. That's a good story over beer, how we stumbled down in the darkness. And another good story over beer is how I smuggled some samples for Yuri Turan through US Customs and Mexican Customs. But unfortunately, virtually we cannot share a beer. So, well, I suppose we could, but it's a little early in the morning here. So anyway, I'm very glad to be here, and I'll start right away. There's an awful lot to talk about, so I can't talk about everything, but better to leave some for discussion. At the end, I'll make some suggestions about what we might want to discuss further, and you can decide. So anyway, here we are. Now we're virtually at Krafla caldera in northeast Iceland. Most of that field of view is the caldera. What's in the foreground is the very beautiful VT crater. VT means devil in Icelandic. And it formed in 1728. It's a phreatomagmatic explosion, which brought up not only a lot of caldera fill, but also class of juvenile rhyolite and basalt. So everything is down there, and we could call it the Discovery Magma Well is very close by, and the magma in that well matches very closely what VT Crater brought up almost 300 years ago. Okay, so this is opening night, and the opening night show is not always the best, but maybe it's more spontaneous. I got about a dozen talks so far signed up after this, including Chile and Hawaii and so on. So it's going to be exciting. I hope to learn a lot. But I want to tell you quite a bit, because I find that a lot of people in our field don't realize that drilling has already sampled magma at depth and provides some really interesting insights. Here's the caldera in yellow and the approximate area of where the shallow rhyolite magma body is, and that bar at the lower left is about one kilometer. And kind of a little left of the center of view is VT Crater, which you saw before. We were looking across there to a parking lot, and the magma well is down here. Actually, there's more than one magma well. Well, this is something I never expected to see in my career, or my life for that matter. That is samples of magma actually quenched at depth and brought up by drilling. Well, early in my career, I expected to see it because advances were going so fast in many fields. But then I also expected to see samples returned from Mars. So that didn't happen either. But now we have magma, and in some ways, that's even more exciting because it's a planetary, a silicate planet regime that we have never seen anywhere. And it's only 2,000 meters below our feet. Now, Krafla is not the only one, the only place where this has happened. But all of them are at about 2,000 meters depth, which is kind of surprising, because who would have guessed there was magma so close to the surface? Power plant in Puna, Hawaii, which is on the east rift of Kilauea, entered dacite magma, which has never erupted on the surface of Kilauea, at about 2.5 kilometers depth. And more recently, Menengai caldera in the East African Rift in Kenya, there seems to be magma all below the caldera at a depth of only about 2 kilometers. It's cyanitic or trachytic magma, if you prefer, but it's right there under the hydrothermal system. And for all we know, there may be many other occurrences that geothermal companies don't want to, haven't publicized, because after all, it might not be good news to investors in a geothermal project to know there was magma lurking under their property. Well, we have imagined things, and that's one thing I want to emphasize to kind of get you excited about perhaps drilling your own scientific holes in magma hydrothermal systems. But we've been drawing cartoons about these things for decades, so much so that we might assume that we actually know something about them. Here's one from 50 years ago. And the thinking hasn't changed a whole lot. You basically have, on the left panel there, you see what's controlling the hydrothermal system. It's basically recharge, then heating, and it's generally limited by the boiling point curve as a function of depth, and the fluid is under hydrostatic pressure. Then down here, starting here, we've got magma, and we have again, we have a shell temperature gradient because the magma is convecting. But in between, we have a conductor. We have hot rock, which acts as an insulator. Why? Because in hot rock, you don't get cracks. You're going to be above the brittle ductile boundary, and so cracks won't stay open, or so people think. And you can imagine, though, that this amount, this distance, which nobody had a clue about, well, they had some clues. People wrote learned papers about the depth to magma, but we didn't really know. And that distance is critical because, you know, it's the thickness of an insulator. And we know that the transport of heat by convection, whether that's water moving or magma moving, is enormously more effective than conduction through solid rock. So we have to look at this interval as really the rate controlling state of how fast the heat gets out of the magma in the hydrothermal system, into the hydrothermal system. It also controls how fast information, that is a perturbation in the convecting magma, how fast the hydrothermal system learns about it, for example, new magma coming in, or if we start sucking geothermal energy out of it, and that's actually a significant amount in terms of energy in a volcano. If you do it long enough, suppose we start depleting this resource, how long will it take the magma to feel the chill? So these are very important concepts, although they're ones that we never talk about because the way it's worked out is magma seems to have fallen mostly into the academic world and hydrothermal systems, because they're economically valid, have fallen most into the corporate world. And these two groups tend not to talk to each other very much, which is unfortunate and something we should do a lot more. And I understand you have a group there at UNAM that thinks about both things at the same time, which is commendable. The hydrothermal part of Krafla and many other hydrothermal systems is very well known because people have drilled it a lot to find out where they can get steam. At Krafla in the caldera, which is a medium-sized caldera, there are more than 40 boreholes. And so these are real temperature contours. People really know this. I mean, it's not a model, it's not speculation. It's the real thing, directly measured. And then, of course, you know, from logs, you can get all other kinds of information on temperature, permeability, and density, and so on. And from cuttings, usually, you can also get detailed information about the lithology. So we know a great deal about these things. What we didn't know until the late zeros, almost 2010, is that if you drilled just a little bit deeper, big surprise, magma. Magma almost at its liquidus, pure rhyolite melt at probably 900 degrees Celsius. And here we're at maybe 400. So you see there's a big jump in conditions. And you might say, why do people stop there? Well, it's good enough. Drilling is very expensive. And if you got enough steam to make money, why go any farther and risk your well? And in fact, one of the big areas for development is we still don't know quite how to handle this. We only know that you get an order of magnitude more thermal energy output than you do from one of these wells. But we need to solve problems of corrosion and high temperature and so on. Anyway, this is an incredible surprise to people. So one thing we might ask first is, what's the problem with magma geophysics? Why couldn't they see that? This deeper hole, the Iceland deep drilling program, well number 1, was very carefully cited. Well, the problem with magma geophysics, if we call it that, prospecting for magma, is that it's never ever been tested against reality. Now, geophysics looking for oil and gas isn't always perfect, but at least, you know, you drill a hole and you find out whether it's there or not. And if it's not there, then you go back to your model and you decide how you missed it. Well, that has never before happened with drilling into magma. So people had no way to say they were right or wrong. The only test of right or wrong was whether you submitted a paper and whether the reviewers agreed with you or not. That was the basis of truth. Well, so it turned out that geophysicists saw, and I don't mean to pick on geophysicists here, but they saw magma where it wasn't. In the US, we went through a careful selection process in the 90s about where we might find magma. And everybody agreed, you know, whether it was a petrologist estimating pressure, or it was the magnetotellurics people, or the seismologists, or the gravity people, they all agreed that this big 700,000 year caldera on the eastern front of the Sierras, which had erupted, which had had a super eruption, was the best place to find and drill to magma in the United States. So we have this giant balloon, and people drilled to 3 kilometers, hoping to go much deeper. But at 3 kilometers, the temperature was only 100 Celsius. Now, that made it one of the coldest holes in Western United States. So you wouldn't expect to find the coldest hole in Western United States immediately over this big magma balloon. And that really led to the death of the giant balloon phase of magma thinking that I'll talk about in a minute. Now, geophysics also couldn't see magma when it was there, and that's the reason for these accidents. Here in Krafla caldera is the plan for this deep hole, and they wanted to get to supercritical fluid because that has an order of magnitude more energy in it than regular conventional hydrothermal fluid. To do that, that is aqueous fluid beyond the critical point, the boundary between vapor and liquid for water. And so beyond that, there's no discontinuity between vapor and water, liquid water. So you have to get high pressure before you get hot to do that. And they didn't. Instead of getting 450 degrees at 4.5 kilometers, they got 900 degrees at 2 kilometers. You'd think they'd be ecstatic, but these companies had gotten together. These boreholes are very expensive. This one was 20 million. They'd gotten together and they agreed that each country would drill to a certain depth, and then the whole group would join in. And then when that hole was finished, they moved on to another company's territory. So they didn't really have the option to stay and study this. But that's what a large group of us, to which you are welcome to join, the Krafla Magma testbed is trying to do. So now that we have the answer, now that we know where magma is, we can go back and see, why didn't we see it in the geophysics? Well, it turns out we did. So people have gone back, particularly the seismologists, they've done tomography, and there indeed is the rhyolite magma body just below the magma discovery well. And other seismologists have seen a nice reflector right at the top of that rhyolite magma body. Well, when you're looking at all kinds of signals and you don't have a clue where your target is, without this ground truth, it's understandable it wasn't found. Well, a great deal more was learned from it than that it was there. For example, temperature is a function of depth. Here's what the old guys, and I'm sorry, they were all guys back then. Fortunately, that is changing. We saw this before. You've got hydrothermal circulation here. Then you've got the conductive gradient to magma. But instead of that conductive insulating interval being 2.5 kilometers thick, it turns out it's 25 meters thick. It couldn't be more than that. It could be even thicker. So now we have something very important. That's a temperature gradient over the top of the magma body, which, if you know the conductivity of rock, which doesn't, for most kinds, doesn't vary a whole lot, and we know what the rock is down there, that gives us a heat flux of 25 watts per square meter, which is pretty significant. So we've got this, and this isn't even an equilibrium temperature, it's an extrapolated estimate from sensors. And this is a petrologic estimate, which is fraught with uncertainties, generally guessed to be about 900 Celsius, but really you could easily put it 50 degrees above or below that. Now, Icelanders have an interesting habit in geothermal. I was always taught when I was learning about drilling, you never drill blind, that is without circulation, without cuttings, because you don't know what you're getting into, and the cuttings might kind of grab you because they're not coming out of the hole. Well, Icelanders are very brave people living in a harsh land, so they don't care. They just keep drilling. So fortunately they did. They hit magma. How did they know this? The first clue was that the formation was soft. The second clue was it pushed back on them and they lost 50 tons of weight from the drill string. Also, the hole got shallower with time, and then they got stuck in it. Well, when they got stuck in it, they got circulation and they got up some chips. Two of them, two lithologies, partially melted felsite, which is basically microgranite. It's the crystalline equivalent of this magma, and just slightly crystallized, near liquidus rhyolite. And you can see that these are nice euhedral crystals, plagioclase. This is silica content, so this is all melt. These are pyroxenes, that's a oxide. And so lots and lots of melt. Here, presumably from the roof, but we don't know the spatial relations because this is just cuttings. We see quartz, that's 100% in SiO2. So these are elemental maps, electron microprobe, sodic plagioclase, and right along the borders is basically a eutectic melt. It's rhyolite. Well, this warms the heart of an igneous petrologist because you see it's not just the bulk system that knows how to melt at the eutectic. It's down at the grain by grain boundary. It has to be at the grain boundary of two different kinds of grains because that's where the ingredient for the melt is. Now, interestingly enough, though, what's not evident from this element map is you've got to add water too. Otherwise, the melting would occur at a much higher temperature. It wouldn't be possible. So you might ask, how is it possible to drill magma? I mean, or even this soft stuff with melt in it. I mean, it's you can't drill water very well. Well, you can drill ice. That's because, of course, drilling is a process that involves brittle fracture of the rock and then getting the fragments out. Normally, in geothermal and oil and gas practice, it's done with these tricone bits, and that just chews everything up, and the return circulation brings you up these fragments, which you can more or less, because you know what the travel time is, you can more or less figure out where they came from. Mostly they came from where you're cutting things right now. But you lose a lot of information in that. The best thing is to get out core, because then you get big samples that you can see various kinds of mineralogical gradients that were in response to temperature gradients. You can see veins and all kinds of stuff. And you know exactly where it came from. But you don't drill big holes this way usually, because that you need for production. And also it really slows, it's expensive and it slows down your progress. So only when they want something very specific will a geothermal company stop and core. Well, but coring of molten rock has been done many times, especially at Kilauea Iki Lava Lake in Hawaii, which formed in 1953. And here's a nice sample of core, now enshrined at the Smithsonian, where Giovanni is. And here's a cross section of the lava lake, about 130 meters deep, 640 meters across. And more than 20 years later, here's the melt present zone, the melt lens, as we call it. So I had the privilege fairly early in my career of kind of sitting this well and measuring the ancient practice of measuring refractive indices of glass in oils and deducing the silica content from that, which worked pretty well. So we could tell where we were in this melt lens immediately. This was really exciting stuff. And it's the reason why I've been obsessed with this for the rest of my career. So this demonstrated coring by quenching melt ahead of the bit at up to 1150 Celsius. And doing it over and over again revealed, really hard quantitative data of crystallization in time, space, and temperature, and mechanisms of heat transport. Well, here's one interesting result. This is a liquid line of descent. You see, this is the melt in those core samples, and it goes from here, where the sample was mostly melt, now glass, to here, where there was just a tiny bit of residual rhyolite melt. It was mostly crystallized, and the temperature going down. This is pretty high temperature because it's anhydrous. And this is a good time to remember that bulk composition and melt composition are not the same thing. We call magmas by their bulk composition, whether basaltic or rhyolitic. But during this, the basaltic composition, bulk composition has changed at all. It's the melt that's changing composition during the crystallization process. That's fairly elementary, but it's worth reminding ourselves now and then. Another great thing that came out of it was a temperature profile as a function of time. And I've just drawn lines through this linear portion of the profile, which is that conductive zone. And here's the final conductive zone. You can see it's only about 10 meters thick, and it has a very high thermal gradient, 84 degrees per meter in the conductive boundary. It also shows, notice that this is really an extremely distorted version of what the old guys thought is the almost isothermal. This is the convecting hydrothermal zone, convecting at 100 Celsius, and then the very steep conductive gradient, the cap on the magma body. One thing they didn't realize, and no thermal model to date has really incorporated this, is thermal fracturing. This surface was obviously moving down in time. That's because when you have such an extreme drop in temperature, there's a big volume change. And the only way the rock can respond to that is cracks. That's how you get columnar joining that you see all over the place. And that's how the hydrothermal system can invade the magma system. Magma system may be retreating, but the cracks are chasing it. And that means that you don't have a growing insulator at the top, which would mean that the thermal output would decline with the reciprocal of the square root of time, but rather you have a downward moving layer which maintains a constant thermal output and a much higher rate of cooling. Well, we can play a game with this. And by the way, I'll send you references and some more information when we're done, but I tried to tack them in here. These aren't complete, but I have a paper. There's a special issue in Geosciences 2020 that has a whole bunch on magma hydrothermal interaction, including my paper on the Kraftla magma. Well, the growth of the crust is a proxy for the amount of thermal energy coming out of the crust. A pretty good proxy. And the other indication we have, an even more direct one, is the thermal gradient, because if you know the rock and you know the thermal gradient, you have the heat flux. So take the heat flux run it for a period of time, how much crust should you crystallize? How much crust should you form? This gives a value of you should be growing crust at a rate of 2.4 meters per year. The actual observed growth rate is 2.3 meters per year. It's pretty good agreement. In fact, it's too good agreement given the some of the uncertainties, but I don't mind. Well, that works for Kilauea. What about for Krafla? We can play the same game. Here it's 24 watts per square meter coming out of the top of the magma chamber, and predicting a crystal growth rate of almost a meter per year. Well, that's not happening, and that's a big point. There's no crystal growth going on. In fact, it's negative. The roof is melting. So why does the heat flux crystallization balance not work for the roof of a magma chamber? Well, magma chamber is not a lava lake. Lava is erupted and degassed at 1 atmosphere of pressure, so it's almost 0.8% water. Krafla magma sits at over 50 megapascals, 500 kilobars, and 500 bars, sorry, and about 2.8% water. Lava is closed to new input of heat and mass. It's rootless. The magma chamber is open to new input of heat and mass. Lava cools through its roof and floor. Magma chamber cools mostly or entirely through its roof. It may be orders of magnitude bigger. And the biggest resulting difference is that a magma body likely convex, although in getting into this, I found there are a lot of convection deniers still in the world. Through the first half of its crystallization history, a lava lake only briefly when first formed. And this is probably a good place to make sure we're talking the same language here. Most petrologists, when they say magma, meaning a suspension of crystals and maybe bubbles in melt, sometimes just pure melt, but that's a special case, but capable of flow and eruption, which we usually assume requires more than 50 volume% melt. Geophysicists would just say, call it partial melt if they think there's a volume with some of those properties. Partial melt for petrologists means a rock that's beginning to melt, may produce a magma by melt segregation step, but isn't really a magma yet. Geophysicists would then call it partial melt as a general term for the melt present region. Mush, which has become very popular with petrologists over the last couple decades and hasn't infiltrated geophysics world very much, is magma now in the crystallizing process, or it could be crystal accumulation with more, I meant to say less than 50 volume% melt, more than 50 volume% crystals. So it's not capable of flow or eruption, which means it's something we never see at the surface. So here's a brief history of thought. The simplest beginnings based on Bowen, who brought applied material science and thermodynamics to petrology, was just crystal settling. Crystals are denser than melt, usually. The problem is, and that works fine at the basaltic end, but at the rhyolitic end, the melt is very viscous. The crystals have a very low density contrast, and you can literally wait until hell freezes over or the magma freezes over, to expect much crystal settling. So that was abandoned largely 50 years ago when people recognized huge eruption volumes of crystal poor rhyolite with apparent chemical gradients that meant some kind of differentiation was going on. And so this was the beginning of what I call the giant balloon phase of igneous petrology. One of the prominent authors in this was Wes Hildreth, starting with Long Valley caldera. He did a process of elimination and got rid of every differentiation problem except something nobody had ever thought of, the Sorey effect of extreme heat flow driving diffusion up chemical gradient as opposed to where it should go. He repudiated this about a decade later, but various embellishments occurred with combining chemical double diffusive convection with melt segregating at the boundaries, causing a rhyolitic cap to develop, while thermal convection in the other direction stirred up the deeper, churned up the deeper part of the stomach. But the balloons burst, and I'm afraid I was party to balloons for a while. But in the US, scientists got together and said, where is the best place to find magma? Well, all the various practitioners, whether it was petrology or seismology or magnetotellurics or gravity, said Long Valley caldera, huge magma balloon under that. So as part of the Continental Scientific Drilling Program, we drilled a hole to 3 kilometers right above this thing, which was inflating at the time, by the way. And the temperature at 3 kilometers was 100 Celsius, making it one of the coldest wells at that depth in Western United States. So we set the opposite kind of record from what we expected, and that was pretty much the end of the search for magma in the United States. But this had broad, this and other things had broad implications for thinking about magma bodies. Attention turned away from mostly melt-rich bodies to mush that could briefly produce melt-rich bodies that would then erupt and escape detection by geophysicists. There's a simple mush model that just produces a pure rhyolite melt layer and then erupts it. There's calculated mush model that has little pods. So here we get chemical diversity without the extreme, which I would say incorrect assumption that when you have diversity in magmas, it all has to come from the same magma chamber. And then very recently, here's classical mush forming at the bottom with some special things going on at the insulator, but growing in from the roof. Anyway, in all these cases, you got mush in the roof. Whereas at Krafla, and in fact, in the other places where magma has been accidentally encountered, you don't go from solid rock into mush, into crystallizing magma. You go from solid rock, or in this case, partially melting roof, into magma that hasn't crystallized, or at least very little. There is no mush. And that is kind of a paradox. And these are just photomicrographs of the other occurrence, Menengai, Puna. It's all glass, right at the top, right where you have to get the highest rate of heat loss, you get the least amount of crystallization or no crystallization going on. Well, what's going on? Well, I think yet to be proven is its vigorous convection, driven by a combination of cooling, crystallization doing cooling, loss of volatiles at the top end of this cell, which is required. You've got to add water to melt the felsite, not just heat, because dry melting of granite doesn't work. Just add water. If you want to make rhyolite, add water and cook until to desired taste. So all these things tend to carry a returning limb of the cell back down while releasing heat and water at this boundary layer. And that's important from the geothermal standpoint, because it means you're continually delivering heat right to the bottom of the hydrothermal system if you have an active body. Well, what does this mean? It means we have a long way to go. And I'm checking the time here. I think we're all right. We have a long way to go to truly understand magma, but we now have a glimpse of what we could get out of how much more could we get out of a scientifically planned hole, which would put down sensors and get equilibrium temperature measurements in core than from an accident where people, oh, we got magma, we got to get out of here. Also point out that since the international program is called the Continental Scientific Drilling Program as a complement to ocean drilling, there's nothing more continental than figuring out how the granitic framework of continental crust forms. So we need to go back to magma at Krafla, and I hope some of you will be inspired either to join us or pick your favorite volcano in Mexico or someplace else and core the solid rock magma transition. That's the real key. Measure equilibrium temperature profiles, and eventually we can experiment with extracting magma energy and instrument magma to forecast eruptions. In the volcanic hazard business, we're only measuring proxies for what the magma is doing. If we can actually get sensors down there, which is completely reasonable given the push for extreme sensors happening now for combustion engines and planetary missions. If we can actually get sensors down there, then we can actually know what the magma is doing. Not only will we then know what these proxy signals mean, we'll also know what the geophysics means. So what are the thrusts here of going to magma in general, or in what we're close to doing now at Krafla, is the fundamental science of silicic magma formation, storage, crystallization, eruption. The energy supply via supercritical fluids that would make geothermal energy an order of magnitude more productive than conventional energy. Right now, it's a wonderful green source of energy, but it's less than 0.5% of electrical power production globally. It could be much more, especially with some critical places that have volcanoes. And we'll get direct quantitative measurement of magmatic conditions. For example, lots of eruptions seem to be triggered by new magma coming in. And we should see a pressure rise first, a temperature rise as mixing starts to go. This would be fantastic. So in conclusion, chemical engineers and magma scientists really need to get together, really understanding the fundamentals of the magma heat source. And I am ending there, and we can have a discussion. Some things you might want to ask about, but don't limit yourself to this, are what's going on in Continental Scientific Drilling Program? How could I get into it? Energy storage in magma versus hydrothermal reservoirs, supercritical fluids. Many companies are doing this, but there are lots of engineering problems. Origin of craftfluorite, other places to look for magma, and can magma become an important green energy source? Thanks very much for your attention.
Thank you very much, John. It was extremely interesting, and I'm sure that many of us in the audience never figure out about this thing to encounter magma during a drilling project. So there are some questions here from the audience, and I'm going to read some of them. One of these questions is, what's your opinion about what's the heating element or the heat source on geothermal fields that haven't had an eruption in the last 10,000 years? I mean, in summary, what do you think is the heating element that maintains active geothermal system that it's being exploited for geothermal energy?
Well, one of the interesting things is that in these places, like Krafla has not erupted rhyolite magma in 10,000 years. Askja volcano, which is nearby, it's a very similar caldera, erupted half a cubic kilometer of rhyolite magma in 1875, but it hadn't erupted rhyolite magma in 10,000 years. And Menengai caldera had not erupted trachytic magma in something like 30,000 years. Kilauea had never erupted silicic magma. I think the lesson here is just because something hasn't erupted a particular kind of magma in 10,000 years in no way means that system is dead. It's it's the top of a extensive system of a chimney of magma and mush that goes all the way to the mantle, and it's kind of hidden beneath a hydrothermal system, but it's taking energy out of that system. So what this clearly shows is that we were wrong in assuming you're safe after 10,000 years, but also that these silicic magma bodies are apparently quite stable in the crust. They're quite happy to sit there for a long, long time, maybe turn into a granite pluton. And it takes a real kick, like a bunch of basalt coming up, like what happened at Pinatubo, to get them to burst forth. So okay. I think the case of these long dormant things, the heat source is still magma. It's just being peaceful.
Okay, great, thanks. Here we have another question, and it's about the crystal mush. And it's about what's your opinion about the crystal mush and all the geophysical and computer modeling about the origin of the crystal mush? Because at the beginning there was a crystal mush under every caldera, and now crystal moshes are being proposed even for every single stratovolcano. So what's your opinion about that?
Well, my opinion is that it's kind of a, oh, can't go all the way back. Oh, well, doesn't matter. It's a bit of a fad, like the balloons were. Everybody's working on mush now. 40 years ago, everybody was working on liquid differentiation in giant balloons. The reason why people went to mush is they didn't find the giant balloons, and well, nobody has found mush. There were good thermodynamic arguments for it being there. So, and yeah, so I think that's why. Now, admittedly, this is one reason for more drilling. And one reason why you have to drill to solve these problems. You can't just build castles in the sky about balloon or mush, because, okay, now we got 3 places with no mush at the top of the magma chamber. We need some more cases to know whether this is a general case, or is there something special like this, or what?
Okay. Well, here we have another, that if there is any field evidence for hydrothermal alteration on the surface on the places that were encountered magma during the drilling. I mean,
yeah, all these places are hydrothermal alteration at the surface, which is why they were drilled. And yeah, so so there we have hydrothermal alteration above the magma body. Whether that's always the case or not, I don't know. But anyway, that's why there was a lot of drilling there. There was a lot of hydrothermal activity at the surface.
Okay. Bueno, a toda la audiencia, si alguien tiene otra pregunta, la pueden inclusive escribir en español y yo la traduzco, no hay problema. Entonces esperamos unos segundos para ver si hacen una pregunta tanto en Facebook como en YouTube, y aquí nosotros la traducimos. Thank you, John. We are going to wait just to see if there is another question from the audience.
By the way, while we're waiting, now I'll get into wild arm waving and speculation. Here's what I'm going too fast here. Yeah. Here's what I think is going on here. We know isotopically that the rhyolite, in oxygen and hydrogen isotopes, the rhyolite looks like hydrothermally altered basalt. So it looks like a 2-step process. And this, for many years, for centuries, almost, people have gone to Iceland because they said, okay, there's no continental crust there, but we have rhyolites and granites, which are the beginning of formation of continental crust, but the source has to be basalt. So maybe this is a sign of how continental crust formed on early Earth. Well, what seems to be going on in Iceland anyway is that we've got, we take basalt, we hydrothermally alter it, which gives it a unique hydrogen oxygen isotope signature, and then partially melt it and extract the rhyolite melt. The caldera is a wonderful structure to contain hydrothermal alteration and also feed this hydrothermally altered caldera fill down through episodes of caldera subsidence down to the hot plate here, where it can partially melt and deliver a gradual accumulation of rhyolitic magma, which is quite stable, similar to densities out here and so on. It's quite happy to sit there and accumulate, unless you got a big eruption coming in, and then you can get some of it moving. Anyway, that's my fantasy, but that's way below how deep we can drill these days.
Okay, here we have another question. This is from Fernando Guerrero. So thank you very much for your talk. In your experience, how computational modeling will help most in addressing the topic of magma hydrothermal boundary? Are process-based models more important than field-based models?
Well, I think we need to do both, and I just presented a very crude first order thermal analysis of what's going on with that conductive layer. Modelers could do far, far better. But I think the key is, to include both magma and hydrothermal circulation with this conductor in between in the model. Well, here's an example, a nice hydrothermal model of supercritical fluids coming off a inert magma intrusion. But magma intrusions are not inert. This thing is convecting, and this boundary is cracking, and so on and so forth. We need to treat magma hydrothermal systems as a single system, and that has seldom been done. Magma is a heat source. Hydrothermal system is the way the heat travels away from the heat source. It's a unacceptable, even though you may have to treat these things differently, it's an unacceptable simplification to separate these two parts of the system. And then hopefully these models can be checked with drilling. You can do a lot more models for $10 million or $100 million than you can do drilling. So there's certainly a requirement for modeling and for finding out what parameters the system is most sensitive to. But ultimately, we've got to drill these things to see if they're right. And what we have so far is that the mush at the ceiling is not right.
Okay, here we have another question. This is from Claudia Pichardo, and she asks, what type of geophysical method do you think can help us better, or which one you will prefer to know that magma is a shallow dike or a shallow seal?
Well, let's not be too timid about it. The shallow magma doesn't have to be a shallow dike or sill. We know very well that the Kraftl magma had to have been there for 30 years because it's all been monitored geodetically since then. And more likely it's been there for at least 300 years because the exact same thing erupted nearby then, and probably for thousands of years. So I think to keep a magma at the liquidus for that long a time, you've got to have a substantial body, and you've got to continue to feed in new magma to the system. And now, as far as what's the best way, well, the two things that have worked so far are seismic tomography and seismic reflection data. They've worked in the sense that they found the magma after the fact, so that was a positive proof of content test. So it would seem that seismology would be the best, maybe the best indicator. I'm hoping that this will attract people to come to Kraftl where we actually know where the magma is and try out or retry various techniques to see whether they see it or not. It certainly looks like temperature gradient isn't that wonderful because you can be 30 meters from the magma and still hundreds of degrees Celsius lower in temperature. So if you took the previous wells and projected to the depth was where magma was found, you would predict 400 Celsius or something. In fact, people did that before they drilled the magma well. They said, oh, we're going to get 400 degrees Celsius at 4.5 kilometers depth. So a lot can happen in a few tens of meters.
Okay, so I will ask a last question just in order to respect the time of everybody, and we will close this seminar. So we have a question from Gabriela Gomez. Thank you very much, a very interesting talk. She said that she would like to know what are the main risks on drilling into a magma chamber or a magma body. Could this depressurize the magma system? And she just wondered, will it be possible to leave a pressure measuring device down there to forecast an eruption? Many thanks for your talk.
Oh, well, you're most welcome, and thanks for the question. I guess that was two parts. One is the hazard risk of drilling into this stuff, and the other was pressure. Yeah. Well, first of all, one could never have proposed drilling into magma before it had been done by accident, because people would say, "Oh, you're gonna kill all the drillers and start an eruption," because nobody knows what magma is like down there. This has happened 3 times by accident without any preparation for such an occurrence. And it turns out that normal drilling practices, keeping a bunch of cold water in the well, handles the problem, because yes, the magma will start coming up because it's on lithostatic pressure, and you've got at best hydrostatic pressure in the hole. And we can see that by the fact that it was lifting up reducing the weight of the drill stem by 50 tons. Anyway, and we can also estimate the magmatic pressure from the water content, about 50 megapascals. So, and certainly if you just had an open pathway to the surface, that would start coming up, it would vesiculate, it would start accelerating, it would fragment, and you could imagine an eruption scenario. But with all that water in the hole, and water has a very high heat capacity, 5 times normal material, including magma, except for the latent heat of crystallization in magma, which is like the latent heat of crystallization of ice. And that's why there's so much energy in this stuff. So that basically turns the magma to glass, first of all, to a cooler thing that can't flow very fast, and then to a obsidian plug. So these wells, it plugged itself very nicely. The other thing, now later there were flow tests, and the wellhead temperature got up to 400, but now the magma is separated from the borehole by an obsidian plug. But there were flow tests with fluid coming out at 450 Celsius at the surface, and that destroyed the wellheads, which and then the well had to be quenched. You couldn't shut it off, so the well had to be quenched by pouring down cold water and taking well casing, 2 kilometers of well casing from 500 Celsius to almost 0 Celsius in a short period of time. You can imagine that destroyed the casing. But anyway, now as far as putting pressure temp sensors down there, that's something we very much want to do. You can't get a pressure temperature off the shelf for 900 Celsius and 50 megapascals, but believe it or not, people are working on it. And well, we can operate thermocouples under those conditions, and because a temperature higher in the hole is quite cool, we can run thermocouple leads up. So we're hoping in the first drilling we can have thermocouples in there for the long term and record recovery to equilibrium and then a good thermal gradient.
Okay, thank you very much, John, for this interesting talk. I would like to close this seminar just saying that we in Morelia, the group of petrology and volcanology, we are working on the same channel as these observations. We are proposing, for example, in Acapulco, that the heating element are that we have like a very shallow intrusions of magma, and we propose that based in experimental petrology and melting inclusions and things like that. We're thinking the same for the Tres Vírgenes volcanic complex in Baja California, where the power company, the National Power Company of Mexico, has a geothermal field active and is producing. So this is extremely interesting, and it's especially it's extremely important for us to get involved in these topics about encountering magma during drilling. Yeah. So thank you very much. We are very pleased to have you here at the Institute in UNAM. And we will keep in touch with you for any questions and trying to make a collaboration and to know more about drilling on magma. Thank you very much.
Thank you. I'd be happy to have a more informal discussion later back and forth about this.
Okay, for sure. I will gather people that we have many interested in our institute, and we can have a discussion more in short with fewer people where everybody can talk and ask you and tell their stories about geothermal systems.
Great.
Well, thank you very much. Muchas gracias a toda la audiencia. En este momento cerramos la plática de John, y como saben, esta plática va a quedar grabada en Facebook, está en YouTube, pueden accederla y volverla a ver en caso de que haya alguna pregunta. Si tienen alguna pregunta que creen ustedes no se haya contestado, mándenme un correo con la pregunta y yo trato de filtrarla a John para el futuro cercano. Muchas gracias a todos, que pasen buenas tardes.